Let's begin to look at the difference between true weight and apparent weight by looking at the situation in which a baby is sitting on a scale. Let's draw a free body force diagram for the baby. Well, the earth pulls down on the baby with a gravitational force. Because the baby is on the scale, the baby is pushing down on the scale, and by Newton's third law, the scale reacts and pushes upwards on the baby with a normal force. Because the baby is stationary on the scale, the size of the normal force and the gravitational force are equal. Therefore, the push of the weighing scale on the baby, or the normal force, is what is read by the weighing scale. The pull of the earth on the baby is known as the true weight. The gravitational force, or true weight, is always constant. It can be found by multiplying the mass with g. The push of the weight scale on the baby, otherwise known as the normal force, is the apparent weight. The baby feels the weight because of the push it feels upwards from the weighing scale. Let's take a look at the situation where the baby is sitting on the scale, but now in an elevator. If that elevator has zero acceleration, it doesn't mean that its speed is zero. In fact, its speed could be constant. It could be moving upwards at 10 meters per second or at 20 meters per second. It doesn't really matter so long as its speed was constant. It'll have zero acceleration. When the elevator has zero acceleration, it means that the two forces acting on the baby must also be balanced. Therefore, the normal force, or apparent weight, must be equal to the gravitational force, or true weight. So in this case, my apparent weight will equal to my true weight. However, if the elevator were not accelerating at zero value, but were accelerating upwards, in other words, its speed was increasing upwards, then by Newton's second law, it'll have a resultant force, or a net force, acting upwards. Since the gravitational force of true weight cannot change, it means that the weighing scale has to push upwards on the baby with a much greater force. In this situation, the apparent weight is greater than the true weight. If, on the other hand, the elevator has an acceleration downwards, that would mean that it has to have a net force downwards. Since the gravitational force cannot change, it means that in order to have a net force downwards, the normal reaction force of the weighing scale on the baby has to be reduced. In these situations, when the acceleration is downwards, the apparent weight is less than the true weight. We feel lighter. You may have experienced this in an elevator. When you enter the elevator and you press the up button, the normal reaction force is bigger in order to accelerate you upwards, so you feel heavier. However, when you press the elevator to go downwards and the lift begins to move downwards, so thereby changing in velocity downwards, accelerating therefore downwards, the normal reaction force reduces lower than the weight, and so your apparent weight is less. You feel lighter. However, when the lift is moving at constant speed, whether it's moving up or down, then there is no net force, there is no acceleration, and therefore the normal reaction and the weight forces are equal. A special value for the acceleration of the lift is when the lift was falling with an acceleration of 10 meters per second squared. Well, if it was falling with that acceleration, it means that it's in free fall. Thereby, the only force acting on it is the gravitational force. For the baby to fall with the same rate, it means that the normal reaction force will have to be zero. Therefore, the weight scale reading will also be zero. The baby's therefore apparent weight will also be zero. This is the situation we call apparently weightless. Does the baby not have a weight? Of course it does. That is the true weight. But the baby does not feel its weight because it doesn't have a normal reaction force acting on it. Now let's do some examples with some values. Let's say the baby's mass was 10 kilograms. That means that the gravitational force, or true weight, is found by m times g, and that will be the mass of 10 kilograms times g, which is approximately 10. So that will be 100 newtons. The gravitational force will be 100 newtons, and that doesn't matter if the lift were accelerating upwards or not, or stationary, or accelerating downwards. Gravitational force will always be 100 newtons. That will always be the true weight. If the acceleration of the lift was zero, therefore, according to Newton's first law, the forces acting on the baby were balanced, that means that the normal force and the gravitational force will be equal. So that means that the baby's apparent weight will also be 100 newtons and equal to the true weight. So the acceleration is zero when the lift is stationary, but it's also zero when the lift is either moving up or down with constant velocity. Let's take a situation where the lift is accelerating upwards at a specific rate of 2 meters per second squared. No matter what the acceleration, the gravitational force, or true weight, will always be 100 newtons. In order to give it that upward acceleration, the normal reaction force and the apparent weight, therefore, must be greater than 100 newtons. We can apply Newton's second law situation here. According to the equation, F net equals m times a. The net force, or the sum of the forces acting on the body, will cause the mass to accelerate. So what is the net force? We're looking at the free body force diagram of the two forces that are actually acting on the body. The net force is the F normal acting upwards minus the gravitational force. So F normal minus gravitational force will cause the mass to accelerate, ma, like before. What we need to find is the normal force in order to find the apparent weight. So the normal force is unknown. It's what we want to find. The gravitational force is still 100 newtons, and that will cause the mass of the baby of 10 kilograms to accelerate by our stated value of 2 meters per second squared. This means that the normal reaction force is 120 newtons. So the apparent weight is 120 newtons. The baby feels heavier than normal. Let us now take a different situation. Let us say the acceleration was downwards, this time with 3 meters per second squared. Well, since the body is accelerating downwards, there is a net force downwards, which means that the normal force must be smaller than the gravitational force. So the apparent weight must be less than the true weight of 100 newtons. We can analyze this by looking at Newton's second law, which states that F net equals ma. The net force in this case is the gravitational force minus the normal force. The gravitational force is larger, so the gravitational minus the normal force gives you the net force downwards. So the net downward force is 100 newtons, which is the gravitational force, minus the normal reaction force, which we don't know, and that causes the mass of 10 kilograms to accelerate by our given value of 3 meters per second squared. This leads to a normal reaction force of 70 newtons. Therefore, the apparent weight in this situation is 70 newtons. Now let's go back to our acceleration situations. When the lift is accelerating downwards, does that mean that it has to be moving downwards? No, it could be moving downwards while speeding up, or it could be moving upwards while slowing down. That is still a downward acceleration. Likewise, if the acceleration is now upwards, does that mean that the lift has to be moving upwards? Well, it could do, but not necessarily. It could be that the lift is moving upwards while speeding up. That will be an upward acceleration. Or it could be that the lift is actually moving downwards while slowing down. In other words, getting ready to stop. That is still an upward acceleration. So in summary, the true weight is the gravitational force, and that never changes on the surface of the Earth. The apparent weight is felt because of a normal reaction force, and so that can vary according to the state of motion of the body. And a special situation called weightlessness, which means that your apparent weight is zero, that is felt whenever the body is free falling with the acceleration of gravity.